So whatever system we consider, this system has acetate ion, H3O, that is hydrogen ion, and acetic acid, right? So now to this particular system, when I'm introducing sodium acetate, indirectly I'm introducing acetate ion and sodium ion. Clear? Indirectly I'm introducing acetate ion and sodium ion. So to the already present, please keep yourself muted until and unless asked to unmute. Okay, so in general, this will have acetate ion, hydroxyl ion, and acetic acid. So because of introduction of sodium acetate, what happens? There is addition of acetate ion and sodium ion. Now what happens is that already present acetate ion is there. Now because of introduction of sodium acetate, there is an increase in the concentration of acetate ion which was already present because we are introducing acetate ion through sodium acetate. Because of this, what happens is that in this particular equation, the concentration of acetate ion in the numerator increases. Right? How does it increase? Because we are introducing sodium acetate, acetate ion concentration in the numerator increases. Even in the system, there is an increase in acetate ion. So here, there is an increase in the concentration of acetate ion. Now what happens? This balance between this Ka and the right hand side, between the left hand side and the right hand side, the balance whatever is there, that gets disturbed because there is an increase in the concentration of acetate ion. To counterbalance, that is Ka has to get neutralized because here there is a momentarily increase in the concentration of acetate ion. So as to balance that, what happens is that to re-establish the dissociation constant of the solution Ka, the hydrogen ion term in the numerator is instantaneously decreases. How does it decrease? This is because of increase in the concentration of acetic acid in the denominator. Okay, so what happens is that whatever acetate ions are there, excess ones, that will combine with the hydrogen ion to form acetic acid. Okay, because of, so as to re-establish the dissociation constant, which was because of increase in the acetate ion in the numerator, whatever hydrogen ion was there in the numerator combines with the acetic acid, that is the acetate ion, whatever excess are there along with that, and it forms acetic acid. So we know that acetic acid concentration increase in the solution now. Again, acetic acid is a weak acid, so it slowly starts dissociating. Okay, so now what happens? Whatever an increase or momentarily change was there between the constant Ka, that is dissociation constant, and the numerator gets stabilized. Okay, so I'll repeat again. On adding sodium acetate, indirectly we're introducing the acetate ion. So because of this, the concentration in the numerator of the acetate ion increases. So there is an imbalance created between the dissociation constant and the numerator here because there is an increase of this. So to counterbalance this, what happens is that whatever hydrogen ion is there in the numerator, they will combine with the excess of acetate ion which has been uh, given by the sodium acetate to neutralize it and forms acetate ion. Sorry, acetic acid. So this particular acetic acid is a weak acid, right? Because it's a weak acid, slowly it starts dissociating, thereby Ka remains unaltered. Okay? And because it's a weak acid, so slowly there is dissociation, so there will not be much changes in the pH as we observe with other cases. So the constant Ka remains unaltered. The ionization of acetic acid is repressed upon the addition of common ion to the solution, and this is known as common ion effect. Okay, so the ionization of acetic acid is decreased on adding sodium acetate, which is having a common ion, which the common ion is acetate ion. So because there is a decrease in the ionization of acetic acid on adding sodium acetate having a common ion, that is acetate ion, this effect is known as common ion effect. So this is only in case wherein both whatever we are considering has a ion in common, that is acetate ion. Okay, so the reduction of degree of dissociation of a salt by addition of a common ion is known as common ion effect. Okay, so the pH of the final solution is obtained by rearranging this particular equation. Ka is equal to CH3CO minus, this was the equation. Just rearrange the equation. Just rearrange this particular equation. So CH3, keep it as it is, Ka as it is. So take this towards left hand side. So it becomes Ka into CH3COOH. And since we are keeping this as it is, this when it comes to the left hand side, since here it's multiplying, it will divide when it comes to left hand side. So it becomes Ka into CH3COOH divided by CH3CO minus is equal to H3O plus. Right? So when we consider this, whatever CH3COOH is nothing but acetic acid, right? So this whole acetic acid we can replace as an acid, because acetic acid totally we are obtaining only from the acid and it's slightly dissociating. So we can, instead of writing that CH3COOH, we can consider the whole thing to be come from an acid only. So whole numerator we can write it as Ka into acid. Okay, and CH3COO minus, even though we are getting it from both acetic acid as well as CH3COONA, that is sodium acetate, but most concentration, since sodium acetate is a salt, it will dissociate completely. We can consider that whatever CH3CO minus maximum concentration, we are getting it from salt only. So we can replace this particular denominator term with salt. So since the acid is weak and ionizes only slightly, the expression CH3COOH may be considered to be represent the total concentration of acid and simply written as acid. When it comes to this, in a slightly ionized acidic solution, acetate ion may be considered of having come totally from salt. Why? Because sodium acetate is a strong salt, right? It dissociates completely. So since 1 mole of sodium acetate yields 1 mole of acetate ion, so you can consider that CH3CO minus totally come from salt. Now you might ask me, this acetate ion, we do get it from acetic acid as well. But what I'm telling is, this acetic acid will not give acetate ion as readily as sodium acetate gives. Right? Sodium acetate gives totally. Like for example, if I'm having 50 molecules of sodium acetate, okay, if I'm having 50 molecules of sodium acetate and 50 molecules of acetic acid, okay, consider both. So this 50 molecules of sodium acetate gives 50 molecule of acetate ion and 50 molecule of sodium ion, right? Sodium acetate gives 50 molecule of acetate ion, 50 molecule of sodium ion. Whereas acetic acid, since it is partially dissociating, you cannot expect it to give complete 50-50 molecule each. Maybe acetic acid, whatever is there, that would have given around 12 molecules of acetate ion and 12 molecules of H plus ion. How about others? Because it is slowly dissociating, it would not completely dissociate at a time. Whereas in this case, as I told, it will completely dissociate, that is sodium acetate. It will give totally, how much ever is the moles of or concentration of sodium acetate, that much only. That is why we are considering totally we are obtaining acetate ion from salt. So this expression now changes to H3O plus is equal to Ka into acid divided by salt. Okay, to this particular equation, if we try to apply log, what do we get? Log H3O plus is equal to log Ka, and this is in the form of log m by n. Log m by n is nothing but log m plus log n. Am I right? Nobody is listening, is it? Log m by n is what? Log m by n is?
log m
Yeah.
minus log n.
Yes. Nobody corrected me when I made mistake. I thought anybody would stop me because I was making mistake. Okay. So this is in the form of log m by n. Log m by n is nothing but log m minus log n. So what do we get? Log Ka plus log of acid minus log of salt. Please keep yourself muted. Okay. So we get log H3O plus is equal to log Ka plus log of acid minus log of salt. So just multiply this particular equation with minus, or just reverse the sign. What do we get? Negative log of H3O plus is equal to negative log of Ka, negative log of acid plus log of salt, because we are reversing the sign. So now what is negative logarithm of H3O plus is nothing but pH. Negative logarithm of Ka is nothing but pKa. And this is in the form of m minus n. What is m minus n? Log m minus log n is nothing but log m by n. So we get plus log of salt divided by acid. So this is the final equation for weak acid and its salt. Okay, common ion effect, or what is the effect of salt on its weak acid? This is nothing but buffer equation or Henderson and Hasselbalch equation for a weak acid and its salt. Is it clear? Anybody has any doubt in the calculation? I mean, derivation. It's very important, very simple. It's for 10 marks. Anybody has any doubt? Now you can unmute and talk, and keep yourself muted when not necessary. Anybody has any doubt? Have you followed? If you do not answer, I assume that you have understood. So at least speak up that you have not understood or understood.
Understood, ma'am.
Okay. All others? So this was buffer equation or Henderson and Hasselbalch equation for weak acid and its salt. I assume that you have understood. So I'll move ahead. Moving on to next. Similarly, common ion effect or effect of, keep yourself muted please. Common ion effect, that is Henderson and Hasselbalch equation for a weak base and its salt. So till now we considered was a weak acid and its salt. Moving on to next, weak base and its salt. So similarly, consider a weak base like sodium hydroxide and weak, a salt which is sodium chloride. So consider weak base. This is weak base, so it dissociates slightly into ammonium ion and hydroxyl ion. If we try to apply law of mass action to this particular equation, we get Kb. Kb is nothing but dissociation constant for a base. Okay, is equal to NH4, concentration of NH4 plus into concentration of OH minus divided by NH4OH. Okay, Kb is nothing but dissociation constant of weak base. So when we consider ammonium chloride, which is a strong salt, it will dissociate into ammonium ion and chloride ion completely, right? So on dissociation, the dissociation constant of weak base, similarly as we talked in case of acid, on introducing ammonium chloride, what happens is that indirectly we are introducing ammonium and chloride ion to this particular system, because of which you expect that there is an momentarily increase in the concentration of ammonium ion. So in the numerator, this concentration increases. So Kb, whichever was constant, is no more a constant. So there is a change in this constant. So as to balance these two, to counterbalance, what happens is that whatever hydroxyl ion is there in the numerator, they get decreased because of a reaction. So this reaction is because whatever hydroxyl ion is there, that is been taken up by the excess of ammonium ion whichever is present. The ammonium ion whichever is present is taken up, takes up the hydroxyl ion which we have introduced. Thereby what happens? Hydroxyl ion in the numerator now decreases, thereby shifting the constant, making it unaltered. So here ammonium hydroxide whatever is there, it will dissociate into ammonium ion, hydroxyl ion, which is repressed upon addition of a common ion which is ammonium ion. Okay, whatever hydroxyl ion was there. So now on introducing ammonium chloride to this particular system, ammonium ion increases. So this ammonium ion increase will disturb the constant which is dissociation constant. So now to counterbalance this disturbance, whatever hydroxyl ion is there, that will react with the ammonium hydroxide to form ammonium ion will react with the hydroxyl ion to form ammonium hydroxide. Okay, whatever numerator hydroxyl ion is there, that will combine with the ammonium ion whichever is in excess to form ammonium hydroxide. So this ammonium hydroxide so formed is a weak base, so it slowly dissociates, thereby on, because whatever hydroxyl ion was there, that is being taken up by the ammonium ion. So this gets counterbalanced with the changes whatever happens of excess, that is excess of ammonium ion is being taken up by the hydroxyl ion, thereby it maintains the numerator, thereby whatever constant is there that will come back to normal. As well, because it is ammonium hydroxide which is a weak base as such, so it slowly dissociates. Okay, because ammonium hydroxide is a weak base, it will slowly dissociate. It is not a single reaction, it has to be a reversible reaction like this. Okay, so this is an example of common ion effect. So similarly for this, if we are trying to apply, so Kb is equal to ammonium ion into hydroxyl ion divided by ammonium hydroxide. Just rearrange the equation, keep hydroxyl ion as it is, Kb into NH4OH, we are taking it this side. This ammonium ion comes to this side, so hydroxyl ion is equal to Kb into NH4OH divided by ammonium ion. We know that hydroxyl ion into hydrogen ion is equal to Kw, right? So hydroxyl ion is equal to Kw divided by H plus. So if we substitute this for this particular equation, we get Kw divided by H plus is equal to Kb into NH4OH divided by NH plus. That is, we are just replacing, instead of OH, this particular term which we have got earlier we would have studied, that is hydrogen ion into hydroxyl ion is equal to Kw. Therefore hydroxyl ion is equal to Kw divided by H plus. So instead of OH minus, here in this particular equation we are just substituting as Kw by H plus. So Kw by H plus is equal to Kb into NH4OH divided by NH4 plus. So now, since this particular base, that is NH4OH, ammonium hydroxide, ionizes only slightly because it's a weak base. So the whole expression we can consider that it is from the base only. Okay, and this, that is NH4 plus, even though we get it from base as well as the salt, again since this particular term is from the salt, the concentration is more, because the salt whatever we are considering dissociates completely. We can replace ammonium ion with salt. Okay, same thing, so we get Kw divided by H plus is equal to Kb into base divided by salt. Okay, apply log for these, we get log Kw. Since this is in log m by n, it becomes log m minus log n. So log Kw minus log H plus is equal to log Kb plus log of base minus log of salt. Just rearrange the equation, we get, we are just taking this log Kw right hand side. So minus log H plus is equal to minus log Kw because it's coming towards the other side, plus log Kb plus log base minus log salt as it is. So this is in the form of minus log of H plus is nothing but pH, and minus log Kw is nothing but pKw, and this is nothing but minus pKb. Okay, because it is plus log Kb, it is minus pKb, plus this is again in the form of log m by n, so log of base by salt. So pH is equal to pKw minus pKb plus log of base by salt. This is nothing but buffer equation or Henderson-Hasselbalch equation for weak base and its salt. Clear? Very, very important. Anything could be asked. What is the effect of common ion on dissociation uh, of a weak base or weak acid? Okay, so why we are studying this Henderson-Hasselbalch equation, what is its use is that the pH of buffer solution can be calculated if the initial concentration of weak acid and its salt, if dissociation constant is provided. The dissociation constant of weak acid or base can be calculated by measuring pH of buffer solution containing equimolar concentration of acid or base. That is, if both these are same, okay, we get log 1. So we'll be able to find this. Okay, so the buffer solution of desired pH can be prepared by adjusting the concentration of salt and acid added for the buffer. I hope Henderson-Hasselbalch equation is very clear. Very, very important for 10 marks. You can expect because it has come many times for the exams. Very important from exam point of view. Any doubt? Henderson-Hasselbalch equation for weak acid and its salt, and Henderson-Hasselbalch equation for weak base and its salt. Or in general, we call it as buffer equation for weak acid and salt, buffer equation for weak base and its salt. Any doubt?
No, no.
I hope you have understood. Okay, so next we'll do it in the next class. But next class, we are going to have a unit test on surface and interfacial tension. Is it clear?
Yes, ma'am.
Okay.